239 seconds. Almost 4 full minutes of silence before the machine types its first character. That number is not from a critic, and it is not from a rival. It is sitting in a table on AMD's own developer site, in the guide that shows you how to run a trillion-parameter language model on 4 desktop computers. Welcome to AI Daily. Today we are doing one story, all the way down. What actually happens when you take an open-weight model far too big for any single consumer machine and shard it across a couple of small AMD boxes on your desk? Not a hands-on impression. The published tables, the memory math, the interconnects, and the numbers the marketing pages leave blank. Start with what AMD actually said. On May 20th, 2026, AMD announced the Ryzen AI Halo developer platform, and the claim in its own bullet points was precise. It capably runs models of up to 200 billion parameters, with up to 128 gigabytes of unified system memory. Pre-orders opened in June, sold exclusively through Micro Center. Jack Wynn, the senior vice president running AMD's computing and graphics group, framed it as giving developers performance, memory, and an open software stack to build agentic systems right on their desks. Reviews landed on July 6th. Storage Review put the configuration at a Ryzen AI Max plus 395, a Radeon 8060S with 40 compute units, 128 gigabytes of LPDDR5X at 256 gigabytes per second, and a price of $3,999. Then AMD went one step further, and this is where the two-box story comes from. On its developer playbook site, AMD published 2 separate recipes for clustering a pair of Ryzen AI Halos. The first uses VLLM with RCCL and Ray tensor parallelism set to 2 to serve Qwen3.5-397B, a 17B and 4-bit GPTQ quantization at a 32,000 token context. The second uses llama.cpp's RPC engine to serve GLM 4.7, a 358 billion parameter model, in a 4-bit unsloth quant that occupies roughly 205 gigabytes across both nodes. So the real figures are 397 billion and 358 billion. Round the bigger one, and you get the headline everyone is repeating. Here is the part that made us want to do this episode. We read both playbooks end to end. They give you the container image, the port for the RPC server, the exact build flags for the GFX 1151 target, the 96 gigabyte Windows VRAM setting, and the 120 gigabyte Linux alternative, and the network requirement, a 10 gigabit Ethernet switch with Category 7 cabling. What neither playbook contains is a single tokens per second measurement. No throughput table. No time to first token figure. AMD published the recipe and left out how fast the dish arrives. That is not an accusation of hiding anything, but it does mean that if you want the speed of a desktop cluster, you have to go find it somewhere else. So we did. First, why any of this works at all? 2 things make it possible. One is unified memory. On these chips, the processor and the graphics unit share one physical pool, so you can hand the graphics side a huge slice of system RAM instead of being capped by a soldered VRAM budget. The second is sparsity. Look at the full name of the model in AMD's own playbook, Qwen3.5-397B, A17B. The A17B is the important half. It is a mixture of experts model, 397 billion parameters total, but only about 17 billion of them activate for any given token. You still have to store all of them. You do not have to read all of them, every token. Capacity is the gate. Sparsity is the key that gets you through it. Now the wall. Token generation on these machines is bandwidth bound. For every token you emit, you drag the active weights across the memory bus, so speed tracks bandwidth divided by bytes moved. The LPDDR5X setup is theoretically capable of 256 gigabytes per second, and the analysis site chips and cheese measured close to 1 terabyte per second out of the 32 megabyte infinity cache. But 32 megabytes holds almost nothing of a 400 billion parameter model, so the 256 figure is the one that governs. AMD's own ROCm blog shows exactly that shape at 4-bit quantization, a 9 billion dense model at 29.84 tokens per second, a 35 billion mixture of experts with 3 billion active at 42.04, and a 122 billion model with 10 billion active down at 8.59. Then there is the link between the boxes, and this is the most under-discussed part. AMD's 4-node guide lists the interconnect as 5 gigabits per second over Ethernet. The 2-node playbooks call for 10 gigabit. 10 gigabits is about 1.25 gigabytes per second, roughly 1/200th of the memory bandwidth inside a single box. That gap is why the llama.cpp RPC approach shows up first. It shards the model by layers, so each node does its slice and passes a thin activation vector onward, rather than chattering constantly the way tensor parallelism does. The community went the other direction. A widely shared setup guide, which drew 232 points on Hacker News in late June, wires two framework mainboards together with Intel E8-10 100 gigabit cards over RDMA, reporting roughly 50 gigabits and about 5 microseconds of latency, versus 70 to 100 microseconds without it, and it needed a patched RCCL library just to recognize the chip. So where do the real speeds live? In a different AMD article, dated February 25, 2026, titled How to Run a 1 Trillion Parameter Model Locally. The setup: 4 framework desktops, each a Ryzen AI Max plus 395 with 128 gigabytes, running Ubuntu and ROCm 7.0.2, linked over that 5 gigabit Ethernet. The model is Kimi K2.5, Moonshot's trillion parameter open model, in a 2-bit quantization weighing 375 gigabytes. There is a nice trick in there too. The BIOS caps dedicated video memory at 96 gigabytes per node, but a kernel parameter pushes it to 120, which is 480 gigabytes across 4 machines. The measured result: 9.45 tokens per second decoding with flash attention on, 8.81 with it off. And now the table almost nobody quotes, from the same article. Time to first token: a 4096 token prompt takes 39.7 seconds. 8192 takes 90.5 seconds. 16384 takes 239.1 seconds. That is the 239 we opened with. Worse, with flash attention disabled, the 8000 and 16000 prompts did not run slowly. They ran out of memory entirely. The article is transparent about it and shows the tuning that helps. Raising the batch and micro-batch sizes lifts prompt processing from 50.16 tokens per second to 100.77, roughly a 2 times improvement. But even doubled, pre-fill is the tax. Decode speed is the number in the headlines. Pre-fill is the number you actually sit through. One more set of numbers, for scale. Storage Review's July 6th review ran the single Halo against NVIDIA's DGX Spark under VLLM at a batch size of 64, which is the serving many requests case rather than the one-user case. On GPTOS 120B with matched input and output lengths of 256, the Halo produced 222 tokens per second and the Spark 701, about 3.2 times. On Llama 3.18b, it was 407 versus 1,330. And at 4-bit precision on that same 8 billion model, the gap blew out to 267 versus 3,573. Read that carefully, because it is the whole thesis. These desktop boxes are competitive on how much they can hold, and are not competitive on how fast they can chew. So what are the alternatives, and are they actually better? NVIDIA's DGX Spark is the direct rival, and it has the same shape of limitation. 128 gigabytes of unified LPDR, 273 gigabytes per second of bandwidth, and NVIDIA positioning it for models up to 200 billion parameters. Same ceiling, AMD quotes. The interesting change is the price. Spark launched at $3,999, and NVIDIA raised the Founders Edition to $4,699, citing memory supply constraints. So the closest competitor got $700 more expensive without getting faster, for reasons that have nothing to do with either company's engineering. Apple tells the same story from the other end. For a while, the largest single-box memory pool you could buy for local inference was the Mac Studio with an M3 Ultra and 512 gigabytes of unified memory. In March 2026, Apple quietly removed that option. The maximum configuration is now 256 gigabytes, and the upgrade to it went up $400. Put those two facts side by side, and the picture flips. This is not a year in which the memory ceiling is rising. NVIDIA raised the price of the same capacity. Apple deleted its biggest capacity. That is the backdrop against which stitching two ordinary desktop boxes together stops looking like a stunt and starts looking like the practical path to a 200-gigabyte model. The community is also finding routes AMD did not publish. One recent write-up describes what it calls asymmetric expert parallelism. Instead of splitting every operation evenly, it pairs a Radeon AI Pro R9700 with 32 gigabytes of fast GDDR6 alongside a Strix Halo with 128 gigabytes of LPDDR5X, then puts the dense path and the most frequently selected experts on the fast card and parks the remaining expert blocks in the big slow pool. On DeepSeek V4 Flash, it reports a median of 51.1 tokens per second against 14.09 for a single DGX Spark, a 3.63 times gap. Take that with the caveat the author states plainly. Each side ran a configuration tuned for its own hardware, with different compression, so it is a whole system comparison rather than a clean apples-to-apples test. Step back, and the real driver is not silicon, it is DRAM. On the Hacker News thread about Framework's new 192-gigabyte machine, an owner reported their equivalent build now costs about $2,000 more than it did last Christmas, purely from memory pricing, and another said their setup went up more than €2,000. A Framework representative replied in that thread that they have no indication of memory pricing coming down in the next year, and many indications it keeps rising over the next 6 months, specifically for the LPDDR5X the desktop uses. Commenters cited supply analyses pointing at a shortfall lasting toward the end of the decade. Treat those forecasts as forecasts, but the direction of travel in 2026 is unambiguous. Capacity is the scarce good. Which brings us to the honest question, who should actually want one of these? The same thread contains a genuinely useful argument. One user wrote that the machine loads big models, but it is meaningless unless you want to wait 40 minutes per prompt, and that the best results came from a 35 billion mixture of experts with 3 billion active, using about 40 gigabytes. Another replied bluntly that if you are waiting 40 minutes, you have no idea what you are doing, describing 1 to 3 coding agents running comfortably with responses in bursts of a few seconds. Both are telling the truth about different workloads. The rule that reconciles them is the one running through this whole episode. What governs your experience is active parameter count and prompt length, not the headline number on the box. On hardware, AMD already told us the next step in that May announcement. In the third quarter of 2026, the Halo platform steps up to the Ryzen AI Max Pro 400 series with higher clocks, up to 192 gigabytes of unified memory and 160 gigabytes addressable as video memory. AMD calls these the first x86 client processors capable of running 300 billion parameter models locally. Framework has already listed a matching desktop with a Ryzen AI Max Plus Pro 495, 192 gigabytes, and 273 gigabytes per second, with no price and no date, and a company representative in that thread conceding it was not their preferred way to announce something. Note the bandwidth, 256 to 273, about 7%. Capacity is climbing. The wall we spent this episode describing has barely moved. 2 things to watch. First, whether AMD or anyone else publishes a proper throughput and time-to-first token table for a 2-node cluster, because right now the official pages give the recipe and the community supplies the stopwatch. Second, the corporate backdrop. Using yfinance closing data, AMD ended June 30th at $580.91, slid to $429.56 on July 29th, then rebounded 13% to $485.39 on July 30th, down about 16% over the month, in a stretch when the whole AI complex was volatile. AMD reports second quarter results on August 4th after the close. We report the numbers and the causes. We do not tell you what to do with them. Nothing in this program is investment advice. So here is the summary in one line. AMD did not overclaim. Two of these boxes really will hold a 400 billion parameter model, and four of them really will hold a trillion. The company published working instructions for both. What the instructions leave out is the shape of the experience. 9.5 tokens per second once it gets going, and up to 239 seconds of silence before it gets going at all on a long prompt. Capacity has been democratized. Latency has not. And in a year where memory is the thing nobody can buy enough of, that trade may be exactly the one a lot of people choose to make. That is our deep dive. If you want more of these, one story, primary sources, the tables, and not just the headlines, subscribe, and we will see you on the next one.